So this is problem 38 from chapter 21. And the question is, if 30 megawatts of power at 45 kilovolts arrives at a town from a generator, and that's the key here, is that there's here specifying that it arrives there, right? Via 4 ohm transmission lines. And by 4 ohms, I took the 4 ohms to be, if each line was 2 ohms, 2 plus 2 is 4. Because you got to have 2 lines going to the town, right? Okay. 4 ohm transmission lines. Calculate the EMF at the generator end of the lines and the fraction of the power generated that is lost in the lines, right? And so, I think Anna did this one, right? The first thing she did was she took the power, which is 30 megawatts divided by 45 kilovolts, and got the current was 666.66666. I'm sorry. Okay. Then she figured out that the voltage drop on those lines was 2.666 volts, right? So that's 2.6666 kilovolts, right? Okay, that's the voltage drop. So if it drops that much, it had to leave the generator at 45,000 volts plus the 2 point whatever, right? You know, okay, 6 volts, right? So that's 47,666 volts, which is about 48 kilovolts, which is what the answer was, right? And then it says what fraction of the total power generated is lost in the lines, and so you can figure out the power lost in the lines. It's always I squared R, right? So that current squared times R is this, that's 1.7. This is 1.7 megawatts, right? And then here she sets it up. Here's 1.7 megawatts divided by the total power is 30 megawatts plus the 1.7 megawatts that's lost in the lines, right? And that ends up being 5.6%. Does that make sense? Yeah? So you need to know that they're talking about the power delivered to the town. Yeah?
Wait, so they're the same. Power gain, power loss is the same thing.
Power gain, power lost. You have to start out, you have to send, if you're going to lose 1.7 megawatts, right, you have to send 1.7 megawatts more down the line, right? So the fraction of the total power is the 1.7 over, not 30, but 31 point, right? Does that make sense? Yeah? You get slightly different answer if you don't add that to the... And then 39 said that we should prove that the power lost is the total power divided by the transmission voltage, this whole thing squared, times R.
Yeah, any versus n, that means total.
Yeah, right. So the way to do that is that you're going to use this. The power loss is always I squared R on power lines, right? And then the substitution is this, that I is the total power divided by the transmission voltage, right? You substitute that in for I, and then you get that squared, and it, yeah? We're going to use that, by the way, for 41. When we solve 41, we're going to use that little shortcut. That's problem 39. Got to demarcate that, right? And then problem 40 was probably your favorite one, wasn't it? If 50 kilowatts is going to be transmitted over 2.1 ohm lines, right? So 0.1 ohms plus 0.1 ohm, I think, is 0.2 ohms, right? And we're going to transmit 50,000 watts, right? How much power is saved if we step it up to 1,200 volts versus 120 volts, just doing it at 120, right? So at 120 volts, what's our current? Because the power loss is always I squared R. right? So what's our current at 120 volts? How do we do that? Is it just 50,000 divided by 120, right? 50,000 divided by 120. Our current is, so we divide those guys, right? So current is power divided by voltage, right? And this gets 416, I'm in scientific notation mode, 0.666 amps, right? Okay. Yeah?
Why is that comes up so much?
I don't know. Okay. Right. Okay. So 416 points. Anyway, whatever, you get the point, right? Amps. And then the power lost is a mere I squared R, right? So it's 416 point, et cetera, right? Okay. Squared times 0.2. So this guy squared times 0.2. And this is a whopping, oh man, what is this? It's 34,722.2 repeating, right? Watts, yeah? So that's how much is lost if you do it the wrong way, and that is keep it at low voltage. Imagine that, right? Okay. Watt. Who is the president of China? The president of China. Who is? That's what I'm asking. I'm asking, who is the president of China? Yes. Who? That's what I'm asking. I want to know. We got to work that one up. I don't know. Okay. That could be a newscast for ASB. President Obama is, visiting with who? No, it's with whom? No, it's with who? No, it's okay. Okay, so anyway, this is how much, and then the question is, class, this is not the hard part. The question was how much more power is lost if we do it at 120 than 1200, right? So let's figure out the power lost at 1200, right? And I'm just going to do back of the seat. I think we could do some more in-depth thing, but I can get the right answer if I just make approximations, right? So the first thing is we don't really know 50 kilowatts, is that delivered or transmitted? Transmitted is easier, so let's go with that, right? The problem doesn't really say that, so I feel that I take the liberty of interpreting the problem the way I want. So I is going to be 50,000 watts divided by 1200 volts, and that is of course going to be 41.666 amps, right? Okay, our power lost just with I squared R, okay? The power lost with I squared R is going to be less, kind of like a lot less, right? So that's going to be 41.666 squared times 0.2. Can we? Yeah, we can move it actually, 100, I don't know, let's, hold on. I don't even know yet. I can't even think, that's higher math.
Wait, so is it supposed to be at 1.2 kilovolts, or is it supposed to be at 12,000?
1200 volts is what it says, isn't it? Yeah, it says 1200 volts. Okay, and then I'm going to square this times 0.2, and I get a mere 347 watts, yes? Okay. Now, what about the 99% efficiency thing? Yeah? Doesn't that mean at every transformer we have to step it up, step it down? At every transformer we're going to lose 1%? About. It's really not quite that, because by the time it gets to the second transformer there's less power to lose, and so we could do something a little more mathematically complex, but I don't feel like it. Okay, so I'm going to say that we lose 2% of the 50 kilowatts in the transformers, right? Which isn't quite true, but let's just go for it, right? So I'm going to say that we also lose 50 kilowatts times 0.02, so that's 2%, times 0.02, which is, of course, 1,000 watts, right? Which is kind of funny. We lose more in the transformers than we lose with I squared R. I wonder if that's always true. And if I add these up, I get that we lose 1.347 kilowatts, right? And then if we subtract the two, right, so that plus 347 is that.